the difference between the lines of the transits is still very hard. But this is where Halley had his best idea. Because the sun is round, the transits will start at slightly different times on different places. Now, Andy, if you could move it so that from Africa Cam, we're just at first contact. As Africa Cam, there, stop. That's perfect. And now switch to Pole Cam, and look, you see, we're miles away from first contact. Well, probably half an hour anyway. It's a big difference. And the two together, you can see that the times are going to be different. So, the brilliant plan was not to have astronomers measure the angles, but simply to record the times of the four contacts. Much simpler, and something they could do much more accurately. Of course, there were more problems too, because the viewing positions change. The chap at the North Pole doesn't move, but the observer down here is going to move 6,000 miles, because the Earth's going to do a quarter of a turn during the process of the transit. So the maths is absolutely fiendish. Now, Andy, you said measuring times, presumably that was local times, was it?
That's right. They could measure local time of when the transits start and stop, but of course they couldn't synchronise their clocks from one side of the world to the other.
They hadn't got Harrison's chronometers by then, had they?
So all they could compare then was the duration of the transit from one location to another, and by comparing those two durations, that's what gave them the distance to the sun.
And how accurate were they hoping to be?
Well, if they could measure those duration of the transit to the nearest second, that would give them the distance to the sun to about 1 part in 500.
That would have been terrific. Did they do it?
No, they're not that accurate, no.
So, armed with this timing method, astronomers geared up for the two transits of 1761 and 1769. They didn't have much trouble getting funding from the government because they thought if they could measure the distance to the sun, it would enormously improve navigation.
For the first transit of the pair, instruments were polished, ships were hired, expeditions were planned to such far-flung places as Cape Town in the south and Siberia in the frozen north. Every journey was hazardous, but particularly so for astronomers from the two nations who were most interested in measuring the transit, Britain and France.
In 1761, the two most powerful nations on Earth, Britain and France, were at war.
Despite the danger, hundreds of astronomers set out for the observing points. Every last one of them suffered for their science, but the astronomer who suffered most was Frenchman Le Gentil de la Galaisière. He set sail for the Bay of Bengal a full year before the transit, but found that his planned observing station had been taken by the British. And a French fleet sent to liberate it had been sunk on a coral reef. In desperation, he sailed further down the coast, but the British had been at it again, and eventually he had to turn around and head for Mauritius.
Unfortunately, time had run out for Le Gentil. He didn't make it to dry land in time and had to watch the transit from the swaying deck of his ship, unable to make any scientific measurements at all.
Rather than struggle all the way back to France just to set out again immediately, he decided to wait 8 years in Mauritius to be ready for the next transit in 1769. Almost unbelievably, on the day, it was too cloudy, and he missed that one too.
He suffered 2 shipwrecks on the way home, and when he finally arrived in Paris, he found that his family had given him up for dead and sold off all his possessions.
Not all the astronomers were so unlucky. The French got good measurements from Siberia, and British surveyors Charles Mason and Jeremiah Dixon got a good view from Cape Town. But they were amazed when they compared notes afterwards to discover that their timings differed by a whole 4 seconds. Of course, it was the dreaded black drop effect. In all, 120 astronomers from 8 nations measured the transit of 1761. But the black drop meant that the timings were of little use. Calculations of the distance to the sun varied wildly, from 77 million miles to 97 million miles.
The 1761 transit had been a disaster. But with another one just 8 years away, there was a second chance for scientists to get it right.
The Royal Society enlisted the help of Master Navigator Captain James Cook, who was sent to Tahiti in the South Pacific. Other expeditions set out for places like California in the west and Lapland in the north. Cook arrived in Tahiti with nearly 2 months to spare, plenty of time to build an observatory, which he called Fort Venus. On the day of the transit, he managed to take a number of useful measurements, but his notes record that he still suffered from the black drop effect. In fact, Cook's times differed from some of his crew's by nearly 20 seconds. After the transit, Cook's orders were to set sail and survey the great southern continent, work that was to extend the limits of the known world and make him a household name. But he was just one of many heroes who risked their lives that year trying to get a good measure of the distance from the Earth to the Sun. And after a thorough analysis, the Royal Society was able to announce that the true distance was 93,726,900 miles. Virtually correct. A milestone in human knowledge had been reached.
And later, we're going to attempt to get our own stardate distance to the Sun by timing the third contact, with the entire live television audience helping out. And you lot too, I hope. Yay! Great. Venus looks just like a featureless black dot when it's silhouetted against the bright disk of the Sun, but transits can reveal a lot of information. In fact, during the transit of 1761, a Russian astronomer called Lomonosov first noticed a white ring all the way around the planet, and he surmised that Venus must have an atmosphere. Scientists watching the transit of 1882 worked out there must be clouds of vapour in the Venusian sky. But what's the planet like on the surface? Now, Robert Massey is an astronomer here at Greenwich. Robert, Venus isn't the sort of place you'd want to go for your holidays, is it?
Indeed not, no. It's probably one of the most hostile places in the solar system. To give you some numbers, the surface temperature is 450 degrees C.
That's hotter than here.
That's even today. If you took a block of lead there, it would melt. The Russian space probes that landed there lasted about an hour before they packed up. Wow. The pressure of the atmosphere is 90 times the pressure on Earth. It's carbon dioxide that we couldn't breathe. And just to cap it all, it rains sulfuric acid. It
rains sulfuric acid. That is terrific. And yet it's supposed to be the planet of love.
Absolutely, and I think that's probably because it looks so beautiful in the night sky. It's a brilliant white colour, it's dazzling. It's the only thing you can see in the sky during the day, apart from the sun and the moon. And so I think for all those reasons, perhaps people gave it that kind of romantic quality. It's seen in beautiful twilight settings.
Why hasn't all the atmosphere burnt off if it's so hot?
Well, if you've got a reasonable gravitational pull, then holding on to a gas like carbon dioxide, which is fairly dense, is perhaps not going to be all that tough. It probably outgassed a lot of that early in its history from volcanic activity. And indeed, we still believe that Venus is probably volcanically active to this day, although not in the same way as the Earth.
But we can't see because of the clouds.
We can't see it because of the clouds, but what we have been able to do is send space probes there that I mentioned earlier. They landed on the surface, survived an hour. That gave us some information. And we can also map it from space using the radar from orbiting satellites. And that's been very effective in giving us a picture of the surface.
And there are mountains and things, are there?
There are very high mountains, basically features that look a bit like continents. There are even impact craters. Even in this harsh environment, some things come through the atmosphere, smash onto the surface and leave craters. And you'd find it hard to believe, but they're still there.
Thanks very much indeed. That's great. Now, the Royal Observatory was built in 1675, not long after Jeremiah Horrocks' observations. And Lucy's up in the original observing room, just up there.
Thanks, Adam. Well, I'm here in the Octagon Room, which has windows on 8 sides and is large enough to accommodate the very long telescopes of the 17th century. However, modern astronomers make use of computers to view their observations, and I'm here in our computer base for this programme. I'm surrounded by a team from the Open University who are constantly monitoring our website, open2.net, and it will be from this room later on that we'll be calculating our very own stardate distance to the Sun. Now, the whole web is coming alive with some fabulous images. Michael, what have you got to show us?
Hi, Lucy. We've had some fantastic images already, such a short time after the first and second contacts. Here's something taken by the Trace Satellite Telescope. It's an amazing movie here. Right,
so this is the satellite which orbits the Earth, and it stands for, I think, the Transition Region and Coronal Explorer. So it's up there in space, away from the Earth's atmosphere. We're getting, I mean, this movie is fantastic.
What I thought was interesting, if we just rewind back here, right to where we touch here, I can't see much of an indication of the black drop effect.
No, I can't either. So we're removing that by having these satellites in space. That's brilliant.
We've also got some images that have come through already from a telescope in the UK here. This is an amateur here. but with some pretty impressive kit, I would imagine.
That's really good. So this is taken, it seems, through a hydrogen alpha filter again. We can see the convection, the bubbling surface of the sun, and a nice filament down there. Now, it's not only Venus that transits the sun, is it? Other objects can too.
Absolutely. We've got an interesting little movie here. See if you can work out what this is.
Ah, right, okay. I think that's the International Space Station there. I recognise the solar panels. So any object which moves in between the Earth and the Sun can actually make a transit.
And there I was hoping you'd say a fly on the telescope.
There you go.
Now, the transit's just about halfway through, and here at Greenwich, I'm with Eddie Yeaton, who is the past chairman of the Flamsteed Astronomy Society. Eddie, what have you got here?
The Flamsteed Astronomy Society is a group of amateurs within the Friends of the National Maritime Museum, and we're up here today looking after the telescopes that belong to the observatory and explaining what's going on to the members of the public.
There are an awful lot of people here. Are you surprised?
I was astonished, particularly early in the morning, even as early as 6 o'clock. This courtyard here was thronging with the number of people around.
It seems to be getting hotter and hotter. I mean, the sun really is hot today, but at least it's clear.
It is indeed. Yes, we've been incredibly lucky, and as long as we don't get any clouds building up over the next couple of hours, it's going to be an incredibly successful day.
Well, luckily, you know, the sun is out, and there are events like this going on all around the country. Here are just a few of them. At Techniquest in Cardiff, they were just beginning to set up. And I was delighted to see that even my old school was keen to get involved. In the heart of Bristol's shopping district, astronomers set up special telescopes on Castle Green to woo early bird shoppers and commuters. Our colleagues at BBC Scotland covered this event near Edinburgh Castle, where pavement astronomers were at hand in the city's shopping district. In the historic town of Chippenham, crowds gathered at the Riverside Park to enjoy the spectacle. So there's a lot of interest in today's transit. Are you all enjoying it? Yeah! That's wonderful. It's amazing to think that the first transit of Venus to be seen was observed by only 2 people, Jeremiah Horrocks and his friend William Crabtree. The next ones, in the 1760s, were seen by hundreds of scientists and sailors. The only other 2 transits to be seen in 1874 and 1882 had the potential to be seen by millions of people thanks to the invention of photography. Here's Vanessa again.
Astronomy had come on leaps and bounds since the previous transits, and a new generation of scientists believed that they had the technology to do the job properly this time.
As well as bigger and better telescopes, the astronomers now had photography on their side. For several years before the transit, scientists were experimenting with new instruments like the photoheliograph. But the most ambitious transit device was invented by the French astrophysicist Jules Janssen.
He invented a camera called the photographic revolver. It allowed a series of 48 photographs to be taken in just over a minute. Now, none of the plates he took on the day of the transit has survived, but these are 2 of the original test plates that Janssen took on a transit simulator shortly before the real event. And so these could be the earliest movies ever made.
It was a great idea, but unfortunately for Janssen and all the other observers taking pictures that day, the technology simply wasn't good enough. The images were too blurred to get accurate readings, and even worse, photography didn't get rid of the black drop effect.
So the 1874 transit was yet another disappointment, and the scientific community rather lost interest.
But the photos did generate plenty of interest amongst the public. It was the public's interest in the transit of 1882 that inspired the Royal Society to ship out yet more observers. And the American Congress ordered another 8 expeditions overseas, even though most of the scientists thought it was a waste of time.
But there's an interesting twist to this tale. An astronomer called David Peck Todd viewed the 1882 transit from Mount Hamilton in California. He wasn't able to see the entire transit as the sun was too low in the sky, but the bit that he did see, he photographed.
Todd took 147 images in total. They remained filed away in the observatory until recently.
And last year, the plates were turned into a movie.
And here it is, By 1882, astronomers had new ways to measure the distance to the sun, so the transit didn't add much to scientific knowledge. But until today, Todd's images were by far the best record of a transit of Venus.
It's wonderful to think that those were the best images of any transit that existed until today. Now here I've got Dr. Adarin Pocock, who's a serious astronomer, and you brought along a wonderfully low-tech instrument. Tell me about it.
It's a bit Heath Robinson, but what I was trying to go for was show that astronomy is accessible to everybody. Fundamentally what I've done is just put a set of binoculars at one end, put a dark box to enclose it, and then projected the image at this end.
Oh, wow. So this is a recycling box.
It is, because I wanted to put the green message across.
Excellent. And we've got a lovely image. It's really clear, and there's Venus, a nice black dot.
Yes.
Are you having a good time today?
Fantastic. The weather's beautiful and it's lovely to be here.
What's really great about today is that not only have we got low-tech instruments like this, we've got really high-tech instruments, even cameras in space. Lucy!
There are several space telescopes viewing the sun. One of them is called TRACE, and that's in orbit around the Earth, so it gets well above the Earth's atmosphere, away from any kind of atmospheric effects. And we've been getting some fantastic movies in from them. This first one shows the planet Venus moving across the disk of the sun, but it's very different to the photographs that have been taken in previous years. You see the whole surface of the sun bubbling and boiling away. The next movie that we've got shows the planet Venus moving against the outer atmosphere of the sun, the very, very hot corona. It's at 2 million degrees, this part of the sun, and you can see the black disk moving across slowly there. It's absolutely amazing. Now, TRACE isn't the only satellite looking at the sun. There's also a satellite called SOHO, and that's placed 1 million miles away from the Earth towards the sun. This is also going to be viewing the transit of Venus, and what it's going to be seeing is in fact extremely useful.
SOHO is a great success story. It's been observing the sun from a stable point in space for an amazing 9 years. It carries 12 different instruments. The British one is called the CDS, the Coronal Diagnostic Spectrometer, and it's designed to investigate how the sun's atmosphere works. 1.5 million kilometres below SOHO is the Rutherford Appleton Laboratory near Oxford. And they've also got a CDS, an identical instrument that was built alongside the one that went into space. The ground-based instrument is connected to a box of tricks called a spacecraft simulator that uses exactly the same connections and software as the real spacecraft. The purpose of the setup is to check any changes to software on the ground before uploading it to the spacecraft. It's much better to discover that the new code causes a system failure here on Earth. Those engineer call-out charges can really mount up in space. Richard Harrison is one of the space scientists who works on CDS.
SOHO is a real Rolls-Royce of a spacecraft. It's designed to look at the sun and study it in phenomenal detail.
It might be a Rolls-Royce, but it's showing its age. And that's just one of the reasons why the transit is so useful.
Now, the reason why it's good for us is there are several things we can do. You can do good science that you couldn't do otherwise.
SOHO sits above the Earth-Sun line, so it sees Venus against the sun's atmosphere, or corona.
Having this disk blocking off bits of the sun's atmosphere bit by bit as it crosses allows you to produce images at a higher resolution, better quality if you like, than we can produce with the instrument we have. On top of that, the darkness of the disk relative to the brightness around it tells you how well the telescope is performing. You can measure the telescope, if you like, in your instrument, the quality of the telescope. And the other thing you can do is to use the different instruments, all looking at the same point. When you see this black disk, you can check on the alignment, the relative alignment of the instrument, which is important, especially after almost, well, over 8 years in space for these instruments.
So a lot resting on getting their transit measurements right.
The whole thing has taken a long time to plan. We plan a long time ahead. You know this opportunity is coming years in advance, in a sense, but obviously for months and months it's a matter of trying to put the plans together to make sure it all works on the day.
And I've got Richard Harrison on the phone now. How are your observations going, Richard?
Hello. Well, we're still waiting. Where we are in space, we will see the transit basically later in time, so it's only just beginning, and it doesn't actually cross the disk. It just goes a little bit south of the sun and crosses through the sun's atmosphere, so that's what we will be seeing. But it didn't start for us until 9:20 local time, UK time, and passes just under the south pole of the sun at something like 2:40 this afternoon. So it's only just beginning for us.
That's terrific. So what are you hoping to see?
Well, we will see a hole, basically, crossing the corona, the sun's atmosphere, and we'll use that for various things, of course, as it crosses through. But it'll just be this dark blob moving across, but across this atmosphere rather than the disk that you're seeing on the ground, as it were. So, it's an extremely useful thing for us to see, but extremely ghostly.
Thanks very much, Richard. Sadly, it turned out that the sun's corona was particularly dim today, and the Soho team didn't see the spectacular new view of Venus that they'd been hoping for. It was almost time for third contact, when Venus was due to reach the right-hand edge of the sun. And, of course, our big experiment, an attempt to get a star-date measure of the distance to the sun. I asked Andy Norton to explain the process. Andy, tell me how this is going to work.
Well, what we want people to do is to measure accurately the time of third contact, when Venus is just about to move off the sun, when it just touches the edge of the sun's disk. But as we saw at second contact, that's going to be very hard to measure accurately because of the black drop effect and the fuzzy edge of the sun and so on. But when people have got that timing, they can put it into our website, where behind the scenes it will be combined with the time of second contact and the times of second and third contact from a South African site. The maths will all be done, and people will get back their own measurement of the distance from the Earth to the sun, the astronomical unit.
Oh, we can actually get each of us our own measurement.
We can indeed. Now, some of those will be too high, some will be too low, but hopefully they will average out, and the people that measured the contact early will be cancelled out by those who measured it late, and hopefully our average measurement will be pretty close to what we know it really is.
Now, you want an accurate measurement. How accurate do you want this timing to be?
Well, if people can make their timing to the nearest second, they can put that into the website and get back their answer.
Wow.
But it will be difficult. It will be difficult to measure.
That'll be really tricky. I mean, we tried this morning, and I reckon it was about 30 seconds after you said. I mean, it was very difficult to tell.
It is. I mean, maybe the best way to do it is to say when it's definitely not contact before and when it's definitely not contact afterwards, and then take halfway between. Maybe that will be a way to do it. People can try different methods and see what works.
Now, everybody here can join in. What we want you to do is to shout now at the exact moment you think Venus touches the edge of the sun. And up in the computer room, every time they hear a now, they'll type in the time. OK, everyone ready? Now, let's have a little practice. 1, 2, 3. Now! Yeah, they ought to hear that. Terrific. OK, Andy, how's it getting on? Could we see the picture from Egypt, please? There we are.
It's nearly there, isn't it?
Very close.
Very nearly there.
But you can still see a little bright bit.
Definitely. Let's see how it looks here, shall we?
Yes. Can we see the white light one from here? Again, very close.
That's probably even
very
closer,
close.
Isn't it?
Right. What does it look like in Much Hool?
Oh, well, we're having a fantastic time here in Much Hool, Adam, with everyone from professional astronomers and PhD students to school children from New Zealand to Tarleton, just up the road. What are you guys up to?
We're just getting ready to measure the third contact.
And how are you going to do that?
We're going to be using stopwatches.
Excellent. Well, we're coiled springs here in Much Hool. Back to you in Greenwich.
Thanks very much. Now, what do you think, Andy?
It's almost there, but
very
not
close.
quite.
Can we see the white light one too? White light one. Oh!
It's almost there, isn't it?
It's so difficult to say, isn't
there.
it? There's a, I reckon, is that black drop? It's
be
very tiny,
on the white
black
light
drop.
Yeah, on the white light
very
image
tiny.
from here.
I reckon it's about... Right, all you don't forget to shout now when you think it happens. Look on the big screen.
It could be any time now.
I reckon there's still
now.
a little sliver of orange light on the right.
On the
there.
Egypt one, there's still a gap, but I think the one from here, that's probably contact around about now.
Are we first here?
I think so, yes. I think
well,
it's contact.
It does look like
here.
it. It does look like it.
Yeah.
Nobody said now yet, right?
But in Egypt...
In Egypt?
It looks as though the edge of the sun's almost sort of bulging round it,
doesn't it?
Is that sort of optical illusion?
I reckon it's about now. I haven't heard a single now from the crowd, not one. We're getting them. Yes.
Look there. It looks as though there's
it's touching.
Contact
there's a little river.
There's a contact there. Yeah.
Right.
I think that's it.
Right. Let's go over to Egypt. Paul, what's it like there?
Well, we're 28 seconds behind you here, so we're going to get third contact any time now. As you can see, feverish activity despite the intense heat. Everybody's getting ready. Video, TV. People are drawing it just like Cook did. Getting ready. Back to you, Adam.
That's wonderful. Well, I reckon we've got it. I reckon we've got first contact in Egypt. And let's have a look at the telescope here. I think we've got first contact here. Ah, hey, look, it's got to be finished.
I think it's there. I think the third contact is there.
Okay, Lucy, have you got any results in?
Hi Adam, we're just waiting for the first results to come in now. We've had quite a few images being sent to our website and people contacting the forum to discuss their results. We've got a couple of images here to show you. So the first one here, unfortunately, an observer had a bit of cloud there, but they're seeing towards the end of the transit. And the next one, we've got a couple more images there. So it's looking really, really good. This is a lovely clear image showing no cloud at all. So we're just waiting for those first observations, the first timings to come in now. Back to you.
Excellent. Well, we'll come back to you in a minute to try and get some results. It was much easier to see the third contact than the second, wasn't it?
I think it was much easier,
It seemed to, I mean, we might have disagreed by a few seconds, but it was much harder.
It seemed easier to see when that contact actually happened, didn't it?
Yes.
They must be seeing that now in Egypt. Well, I think this is the image from Egypt, isn't it? And it looks as though they've definitely had the third contact
I think they must have had the first contact. Now, let's see what our punters here think. OK, here's a couple of likely punters. Now, the sun's up there.
No! Oh, we missed it. We missed it. I tell you what, for the first time ever in our history, Dick and Dom have actually learned something.
Do you know, we came here not knowing what to expect. We knew nothing about it, and it's actually been really interesting.
Fantastic. It is. It's a fascinating thing, isn't it? And anyone can do astronomy, you know, even me.
Yeah?
And that really is
Well, I'll tell you what we're gobsmacked by it. The whole event was amazing, but the most amazing thing was seeing Brian May as an astrologer. That was incredible.
Thanks very much. And if you fancy your chances, you can watch the video on our website for the next few days and see if you can do any better. The first results started to come through to the website pretty quickly.
The results have been coming in here thick and fast onto our website, open2.net. And in fact, we've had well over 300 people accessing the website already, giving their timings. Now, here at Greenwich Observatory, we asked people in the courtyard to shout out when they thought the time of third contact happened. And in fact, they almost all shouted at the same time. So we've input that time into the website, and that gives a distance of 163 million kilometers to the sun. Now, everybody who's been entering their times onto the website have all been contributing to working out the stardate average distance to the sun. And at the moment, that's looking to be 161 million kilometers.
Of course, nowadays, there are other ways to measure the distance to the sun. In 1990, for example, NASA made a direct measurement by bouncing a radar pulse off it. But transits are still very important scientifically as a way to detect planets orbiting other stars. So while we waited